Alright, so we want to go into our second of three videos talking about undoing derivatives. So this one we're going to talk about areas under curves. So to start, this is maybe seemingly unrelated from what we talked about last time with antiderivatives. Okay, so before we get into talking about areas under curves, I want to go and introduce a little bit of notation. The notation isn't necessarily super useful. Well, maybe not useful is the right word, maybe incredibly relevant for us. It will be when you go off to Calc 2, but I just want to introduce it for simplicity here because I'm going to need it to develop some of these ideas with area. Okay, so we know how we could add a few things very concisely. So suppose you're given 3 plus 3 plus 3 plus 3. We would just write that as 4 times 3 because we have 4 3's that we're adding together, so we get 4 times 3. And it's maybe easy enough to write out 3 plus 3 plus 3 plus 3. You don't need to do 4 times 3. But if you had 3 plus 3 plus 3 100 times, it's just much simpler to write out as 100 times 3. And that works really, really well so long as you're adding the same thing. So what we're going to have is a notation to go and add up, we'll say, related things. So we'll use the Greek letter sigma, and we'll have this this lower limit of k equals 1 and this upper part about n. All it's saying is that we're going to add up the thing that's here, so in this case ak, and we're going to do it for each k going from 1, 2, 3, all the way up to n. Okay, so if we want to add up, do regular addition using the sigma notation, we would just go and say the sum from k equals 1 to 4 of 3. And then you could change it even more, and you could have it going as the sum from k equals 1 to 100 of 3. So, so that would go and give you a concise way or different way of doing standard multiplication, really, as a lot of additions. But what this also allows us to do is allows us to add up kind of very related things. So in this case, maybe we want to add up the numbers 1, 2, 3, 4. We could do that by saying it's a sum from k equals 1 to 4 of k. So we're going to add up k equals 1, k equals 2, k equals 3, k equals 4, and when we do that we get 10. Or we could take the function 1 plus k squared and have a sum going from k equals 1 to 3. So it would say we're going to take 1 plus k squared when k is 1, then we're going to add to that 1 plus k squared when k is 2, then we're going to add to that 1 plus k cubed when k is 3. We add all that up, we get 26. Or maybe we have some signs. So we could say we're going to take sine of k pi over 2 when k is 0, plus sine of k pi over 2 when k is 1, and so on up to sine of k pi over 2 when k is 4, and that would give us 0 plus 1 plus 0 plus minus 1 plus 0, which altogether is 0. Okay, so then just a couple of rules. One is that if you have a constant times all of your AKs, we could just pull the constant outside the sum. That makes a lot of sense, because if I add up a whole bunch of things that are multiplied by 2, I could factor out a 2 from everything that's getting added up. And if I want to sum up AKs plus BKs, I could just take the sum of the AKs plus the sum of the BKs, which is, I think, pretty straightforward. Okay, so then some other kind of standard notational formulas. You don't need to know these, but I'm going to want to refer back to at least one of them in a little bit, so I just want to put all of these here so that I could refer back to them if I need to. When you get off to Calc 2, you will see these ones again. Okay, so as we had before, if we sum from k equals 1 to n just a constant, that's going to be our constant times n, because you'd have c plus c plus c n times. If you have the sum from k equals 1 to n of just k, that will be n times n plus 1 all over 2. if you sum up k squared from k equals 1 to n, that's n times n plus 1 times 2n plus 1 all over 6. And then we also have a relation for k cubed. So sum up k cubed from 1 to n, you get n squared or n squared times n plus 1 squared all over 4. So interestingly, the square of that one. Again, you don't need to know these for a test or anything, but I just want to refer back to at least one of them in a little bit. Okay, so we said we want to talk about areas under curves. So let's kind of develop the idea that we want to proceed with. So suppose that we have the function f of t equals 3 and we're going from t equals 0 to t, and we'd like to find the area underneath this curve and above the x-axis. Well, here we're just dealing with a rectangular region, so we'd say we have a rectangle, we have height 3, we have width 2. This gray box is going to give us 6 units of area. Okay, well, that's a very nice function. What about this one? Well, we could do the same kind of thing, but just break it up into 3 different regions. So over here from 0 to 2, we have a rectangle. And over here from 3 to 4, we also have a rectangle. But in between 2 and 3, we have a trapezoid. So we could go and find the area of our rectangles and the area of our trapezoid from standard formulas that we would have. So standard, nice geometric formulas. Okay, well now what about a function like this, t squared plus 1 going from 0 to 1? We don't have clear geometric shapes like triangles or squares or circles or trapezoids or anything. So it's not maybe clear off the top how we could go about coming up with the area for this gray shaded region. But maybe what we could do is we could use what we just did to approximate the area. So for example, let's say that instead of trying to get the exact area, we want to approximate it with just 2 rectangles. Right, so what we'll do is we'll take the interval 0 to 1 and we'll split up the number line into 2 intervals. We may as well make it simple on ourselves and make them equal sides. So we'll have 2 rectangles, both of width 1/2. And now we just want to set the height. So what I'm going to do in the first case is I'm going to go and put the height to be where what the function evaluates to at the leftmost point. So what I mean by that is I've got the interval 0 to 1/2 here, and I'm just going to put my height to be f of 0. And over here, the leftmost point of the interval 1/2 to 1 is 1/2, so I'm going to take the height to be f of 1/2. And when I add up the areas of these 2 rectangles, I get 1/2 for my left rectangle, and I get 5/8 for my right rectangle. Add those up and you get 9/8. So these 2 rectangles give us 9/8 units of area. Okay, so that's fine and all, but it's an approximation. We should at least note whether our approximation is giving us an overestimate or an underestimate. From here, it should be pretty clear that we're losing a fair amount of area right here, and then also a lot over here. So this one's going to give us an underestimate. Well, maybe what we could do instead is put the heights of the rectangle to be where the function evaluates to at the right point of our intervals. So if we do that, we'd say our first rectangle, it's going over the range 0 to 1/2. If we put the height to be where the function evaluates to at the right point, we'll have f of 1/2. And then for a second rectangle, f of 1. And if we do that, we wind up with 13/8 units of area. And here we can see this is going to clearly be an overestimate because we're picking up extra area over here and we're picking up a lot of extra area over here. The third kind of standardish way that you could go and choose the height of your rectangle is to go and split the difference. So pick the height of each rectangle to be what the function evaluates to in the middle of the interval. So we said that our first interval is going from 0 to 1/2. The middle of that is at 1/4, and then the second one, the middle will be 3/4. And if we do that, what we'd see is that we wind up with a total of 21/16 units of area. And here we see is that this is going to give us a better approximation. Still maybe not spectacular, but we're going to be picking up a little bit of extra area there. We're going to be losing some area over here. We're going to pick up some area over here. We're going to lose some area over here. So kind of we split the difference and maybe we get a better estimate. Okay, well the other thing that we could do is if we're not satisfied with the approximation that we've got, we could just take a few more rectangles. So in this case, I have 20 rectangles. And what we could see is that if we were to sum up all of the areas of these rectangles, that doesn't look like too bad of an approximation. Especially over here on the left, it doesn't really look like we're picking up or losing too much area. Over here, maybe we're losing a little bit, picking up a little bit, but not that much really that it's super noticeable. Okay, so what we've really done is we've partitioned the interval in question up, and we've done it with, in the first case, just two subintervals. So we've taken the interval 0 to 1, we split it into the subinterval 0 to 1/2 and 1/2 to 1. And when we have what's called a regular partition, all of our subintervals have the same length. For us, when we were looking at the intervals 0 to 1 with two subintervals, our delta x, so the length of each subinterval, was 1 minus 0 over 2, or 1/2. And then you have what are called the grid points. So these are just all of the various points that we have for the interval. And the points that we had were going to be 0, 1/2, and 1. So I mostly have these expressions because I want to refer back to them in a moment. Okay, so this gives us an approximation for the area with what is referred to as a Riemann or Riemann sum, depending upon how you want to pronounce the German. And the idea is that you can approximate the area underneath a function by just going and summing up the area of all of the rectangles. And that's what we just were doing a moment ago. And you could just take as many rectangles as you like, effectively. Okay, so as I said, the three standard ways of doing an area approximation are to use the left point, the right point, and the midpoint. So these xk stars are what we're putting in here. So what this sum is giving us is the delta x, which is the width of the interval. The f of xk star is the height of the interval. So just height of rectangle 1 times the width of rectangle 1. So the area of rectangle 1 plus the area of rectangle 2, and so on. We have these three ways of doing it. Again, I just put the formal definitions out here because I want to invoke them in a moment. Whenever you're writing these kind of problems up for homework or worksheet or a test, you don't necessarily have to use these formal expressions. You can just kind of do it based on really what I was doing here. Okay, so suppose that instead of doing two rectangles, we used 4. So if we do it with left points, we'll have we'll first break our number line 0 to 1 up into the intervals 0 to a quarter to a half to 3/4 to 1. If we use left points, we're going to evaluate at f of 0, f of a quarter, f of a half, and f of 3/4. And when we add up the areas of these 4 rectangles, we get 39/32, so about 1.22. If we use the right points, again, we'll see that this one's going to give us an overestimate. And when we add up the areas of these 4 rectangles, we get 47/32, so about 1.47-ish. And the other standard way of doing it is midpoints. So we'd evaluate f of an eighth, f of 3/8, 5/8, and 7/8, add up the areas of these 4 rectangles, and get 85/64, so about 1.33-ish. And then we could keep going if we wanted. We could take 20 rectangles here. So if we do that, we get that our left point approximation is going to give us an area of about 1.31. The right point approximation would give us an area of about 1.36. And the midpoint would give us something about 1.333. Okay, and the idea with this is maybe we could figure out from the picture is that as we take more and more rectangles, we're getting closer and closer to what the actual area is. And especially over here, it looks like that as far as the eye can tell, we've got the exact area over here. We don't really, we're maybe missing a little bit or having a little bit too much, but it looks really close. So as we take more and more rectangles, we get closer and closer to the actual area. So what we'll define to be the area under the curve is the limit as n goes to infinity of the sum from k equals 1 to n of f of x k star times delta x. So in other words, what we're doing is we're going to sum up the area of an infinite number of infinitesimally thin rectangles. And again, we'll use a regular partition, so all of our delta x's are the exact same. Okay, so let's do one example of this. So let's find the exact area underneath the curve x squared from over the intervals 0 to 2. Okay, so I'm going to do this using the right point rule, but what's nice here is that it wouldn't really matter which rule we use for the xk stars, but I'm just going to use the right point rule for simplicity. Okay, and when we have n rectangles, our delta x will be 2 over n because our interval is of size 2, and we would have n rectangles. So our a is going to be 0 because that's the left point of the total interval, and our delta x is 2 over n, so xk star is going to be 2k over n. Okay, so the exact area for our function x squared over the interval 0 to 2 is given by this limit as n goes to infinity of the sum from k equals 1 to n of our heights f of xk stars times delta x's. So f of 2k over n times 2 over n. Well, f of x is just x squared, so the exact area is given by the limit as n goes to infinity of the sum from k equals 1 to n of 2k over n all squared times 2 over n. Or in other words, the limit from n going to infinity, sum from k equals 1 to n of 8 k squared over n cubed. Okay, so the first thing that we could do is we could go and start pulling out some constants. So 8 is it's always a constant, so we can pull it all the way out into the front of the limit. Now the sum, the thing that's changing inside the sum is k. If we, inside this sum, n is effectively a constant. As k changes, n doesn't change, so n is constant with respect to k, so we can pull it out in front of the sum but not the limit, because the limit is n going to infinity. So we'll have the area is going to be 8 times the limit as n goes to infinity of 1 over n cubed times the sum from k equals 1 to n of k squared. Now what I want to do is I want to invoke that formula from the beginning for the sum of k squared, and that sum is going to be n times n plus 1 times 2n plus 1 all over 6. Okay, so in other words, the area is just going to be 4/3 times this limit as n goes to infinity of n times n plus 1 times 2n plus 1 all over n cubed. But now we're just back in the realm of finding limits at infinity, and at this point we're pros at that. So we expand out our numerator, we say, hey, we've got a limit as n goes to infinity of a polynomial divided by a polynomial. All we need to do is just look at the ratio of the biggest terms. The biggest terms in the numerator and denominator are both n cubed terms, so we have a 2n cubed in the numerator and n cubed in the denominator. That limit as n goes to infinity is just going to be the limit as n goes to infinity of 2n cubed over n cubed, so just 2, and that tells us that the exact area is going to be 8/3. Okay, so far what we've done is we've assumed that our function is always positive, and now what we'd like to say is, well, what happens if we allow for the function to take on negative values? Well, we could do the same kind of thing. We're just going to have to change one thing. And here it's going to be that we're going to allow rectangles to have negative height. So maybe this seems kind of weird, but we'll have negative height, which will give us the idea of negative area. Right? So what's going on here is we're going to have what's called net area. So all we're going to do is we're going to take the positive area, so all of the positive area of everything that's above the x-axis, subtract off the area of the rectangles of everything below the x-axis. So one way you could think about this is in football, when you have a punter, we have what's called net punting yardage. So suppose that you have a team is punting and they start at midfield and the punter kicks the ball into the end zone. So the ball goes 50 yards. So that's the net distance, or that's the total distance of the punt, 50 yards. But because the ball goes into the end zone, the other team starts with the ball at their 20-yard line after the touchback. So you have a 50-yard punt, but the other team gets 20 yards, so your net distance would be 30 yards. The same idea when you have a punter kicks the ball and then the return team returns the ball. So maybe the punter kicks the ball 55 yards, the returning team returns it 8 yards. Your net distance on that punt would be 47 yards, so 55 minus 8. Same kind of idea here for net area. Right, so in general what we'd have is we'd have the positive areas, so these green regions, and then we'd subtract off the area from this red region, because that would be negative area. And then we could also do that with rectangles. So we would have our positive area would be given by the area of these green rectangles, the negative area is the area of these red rectangles. So we would just go and cancel off the positive and the negative area, and that would give us the net area. Right, and if we wanted, we could do the same kind of thing. To get a better and better approximation, just take more rectangles. And as we see here, when we take more rectangles, we get something that looks like it's almost giving us the exact area. We just would take the number of rectangles to be going towards infinity. Okay, and that gives us what's called a general Riemann sum. So we could have an f that doesn't have to be positive anymore, so we can take on positive and negative values. And also, if you really wanted, you could go and change the size of the of each of the intervals. You could do that. So you could go and make some of the rectangles have width a tenth, other ones have width a fifth. You would get the same kind of thing. You would just be adding up the areas of all of these various rectangles. Okay, so this will lead us into what's called a definite integral. So we'll say that a function f, which is going to be defined over the closed interval a to b, is integrable over a to b if that area limit, so the limit as n goes to infinity of the sum from k equals 1 to n of f of xk star times delta xk, exists and is unique over all partitions of our interval and choices of xk star. So basically what this means is that you could partition up your interval a to b however you like and pick any xk stars inside of the interval, so long as the value you get in the end is unchanged, then everything works nicely. And we'll say that the definite integral, so we'll use this elongated S symbol that we introduced yesterday, but it's different here because we have these numbers A and B stuck onto it. So last time we were using this symbol to talk about antiderivatives, now we're using it to talk about areas. Okay, so if you're given a continuous function or a function that is bounded and has only finite discontinuities, then your function is integrable. And for everything that we're going to do, we're always going to be dealing with continuous functions. So anytime that we're trying to find a definite integral, it's going to be a continuous function over the interval. When you get off to Calc 2, maybe not anymore, so then you have a couple of hassles maybe that you have to take care of, but for the most part, it's not that bad. You'll see that when you get to Calc 2. Okay, so all we've said so far, the only way that we can actually go about finding definite integrals is by using this area definition. If for some reason on any problem you want to do that, you may. I don't recommend it because it's probably a lot more work than you need to do. So one way that we could go and find net areas is by just using standard geometric rules. So for example, we have this function 2x minus 6 going from x equals 1 to 6. Depending upon how you view this region, you could view it as a trapezoid or two triangles, one triangle that's above the x-axis, the other one that's below it. So one triangle with positive area, the other one with negative area. So to see that these are the same thing, I'll go and describe what's going on here with both. So the first triangle that we have, it has a base of 2 and a height of -4. So we have a base going from 1 to 3, base of 2, and a height going from 0 down to 4, or -4, so a height of -4. And our area, so base times height over 2, is -4. For our second triangle, we have a base that's going from 3 to 6, base is 3. The height is going from 0 up to 6, so our height is 6. Base times height over 2, our area for that second triangle is 9. And if we want the net area here, we are going to, well, in this case, I'm just going to add them because I've said that my first triangle has negative area. So the net area here is just going to be 9 minus 4, so the net area is going to be 5 square units of area. But I could have also viewed the region as a trapezoid. My base is going to be 5 because we're going from 1 to 6. The height of one of our legs is 6, the height of our other leg is -4. The area of a trapezoid is the base times the sum of the two heights all divided by 2. And if we put all of these numbers into this area equation, we would also get 5. So we get the same thing regardless of whether or not we view the region as two triangles or just a single trapezoid. Okay, so the other thing that we might have is, well, this one, it's clearly a trapezoid, and we're going from 2 to 4 for the function 2x plus 3. Right, so it's a trapezoid. My base is 2. The height of one leg is 7. The height of the other leg is 11. I put all of those numbers into my area expression, and we get 18. Maybe we have the function square root of 1 minus x minus 3 all squared going from 2 to 4. The function is maybe not obvious what it is, but from the picture we can see that we're clearly looking at a half circle of radius 1 centered at x equals 3. So because we're dealing with a circle of radius 1 and it's a half circle, our area will just be pi times r squared over 2. R is 1, so we get pi over 2. Okay, so then for definite integrals, we have a couple of rules, and maybe these aren't entirely surprising based on what we saw for limits and derivatives. So the first one is that the definite integral, so the net area under the function f going from a to a is 0. In other words, what that's saying is we're going to take the net area underneath some function from, say, 2 to 2. Well, find me the area of a region that has width 0. Well, it's just going to be 0, right? If you had a rectangle of width 0, it has area 0. If you take the net area going from a to b of f of x, that is the negative of the area going from b to a of f of x. So this one is saying that if we go from left to right, and then we go from right to left, the areas are the negative of each other. The reason for that is that if we come back to this expression that's kind of underpinning what we said about the net area, when you go backwards, so you go from b to a, you're just negating all of these delta x terms. So you would have a negative in each term. If you factor it out, you get the negative of what you started with. Okay, if we take the definite integral from a to b of f plus g, it's definite integral from a to b of f plus the definite integral from a to b of g. You know, I guess as we've seen, that's what we had from limits and also derivatives. Constants we could pull out in front. So I guess both of these ones, if we come back to here, so we have an f of x1 star plus g of x1 star times delta x1. Well, we could split that apart as f of x1 star times delta x1 plus g of x1 star times delta x1. So we could split up sums and differences like that. Constants would work the exact same. We'd have a constant times each of these things, factor it out in front. Okay, so this fifth one is saying that you can split intervals up. So you could do a definite integral from a to b. You could write it as a definite integral from a to c of f plus a definite integral from c to b. So in other words, we could take the interval from 2 to 4, we could write as a definite integral from 2 to 3 of this function f, plus a definite integral from 3 to 4. So in other words, the area of a quarter circle plus the area of a quarter circle of radius 1, well, that's going to give you the area of a half circle of radius 1. The sixth one I include more for completeness. It just says if your absolute value of your function is integrable, then the definite integral from a to b of the absolute value is just going to be the total area. So for something like this, it would give you the area of this one plus the positive area of that one. Okay, so then we could take a function like x cubed and plot it from 1 to 2, and what we'd see is we have this negative area over here, this positive area over here. And what we could also do is change this upper limit. So if we say we're going to start with our left point being at -1, and we're just going to slide the right point along the x-axis a bit. So we start at -1/2, we would get this region, we go over to 0, we get this region, and we could keep going. We could go over to 1 and get a different region, or maybe take the one we started with, going from -1 to 2. And what's going on here is we have what's called an area function. So what we'll do is we'll take some continuous function f that's continuous for t bigger than or equal to some a value, and we'll say the area for f with the left endpoint at a is going to be given by the definite integral from a to x of f of t dt. The reason why I'm kind of using x and t in here to be something different is I just don't want to use x or t twice, because then it gets confusing about what t actually means. So here I'm saying x is the right point of my interval and t is just a dummy variable. So this expression a of x is going to give us the net area for the region bounded by our axis over the interval a to x. And if we found this using techniques that we haven't really seen yet, what we would have is that the area function at -1, so just that area from -1 to -1 is 0, and that makes sense from one of the rules we just had. The area from -1 to -1/2 is -15/64. The area from -1 to 0 is -1/4. The area from -1 to 1 is 0. And the area for our region from -1 to 2 is 15/4. Okay, so what we could do is we could just go and use this area function to go and see that some of the things we just said a moment ago with geometric rules make sense. Right, so what we'd like to do is say we're going to take the function 2x plus 3, so that trapezoid that we had from a couple of minutes ago, and what we'd like to do is find the area function for this, and then we can also validate that the area function at 4 will give us back 18, which was what we just found as the area for this region. Okay, so what we're going to have is a trapezoid that's going to have base x minus 2. So if I go and have this trapezoid going out to some point somewhere along the x-axis, where my right point is to the right of 2, the base of this trapezoid will have length x minus 2. The height of one of my legs is going to be 7, so that's what's happening at f of 2, and the height of my other leg is going to be 2x plus 3. Well, when I go and I put all of these things into my area function, we get an area function in the end of x squared plus 3x minus 10. And when we evaluate this function at a couple of points just to make sure that we've got everything, things nicely make sense. What we'd see is that the area function at x equals 2 is 0. That's good. That's exactly what we want. And also the area function at 4 is 18, and that's also what we want because that's what we just found a moment ago. Okay, and now what we're going to do is we're going to introduce what's called the fundamental theorem of calculus. It's also got part 1, which indicates that there's a part 2 coming up. Okay, so the first thing we could do is we could say I've got this function f of t, and it's going from t equals 1 to some point x. Well, what I've done so far is we've gone and approximated the net area underneath f of t from 1 to x by all of these rectangles. Okay, well then what we could do is we could extend it a little bit and find the net area from underneath f of t from t equals 1 to x plus some small value h. So if we see here, the difference is I've added on a small rectangle over here, and we could see, well, what's the difference between these? We're going to add on a small value, ideally a small extra area, right? So this orange rectangle is the area that we just added on. So the area, the net area under f of t from 1 to x plus h minus the area, the net area underneath f of t from 1 to x is approximately h times f of x. So h was the width of this rectangle, f of x is that, that value there. And when h is small, the extra area that we're going to have here is going to be approximately just the area of that rectangle. What we see is that there's a little bit here, but if I took more and more rectangles, the difference would be non-existent. The difference would go to 0. Also, as we make the rectangle thinner and thinner, difference will go to 0. Okay, well, maybe for no apparent reason, I'm just going to go and divide both sides by h. So now what we have is that the area function at x plus h minus the area function at x, all divided by h, is approximately f of x. And now for no reason whatsoever, I'm going to throw in some limits. Or I guess maybe not for no reason whatsoever, but I want to take the width of this rectangle to be small, so that's why I want to take the limit as h goes to 0. Well, when I do that on the right-hand side, there are no h's over here at all, so I just get f of x. But on the left-hand side, we have the derivative, the limit definition of the derivative of the area function. Right, so remember that 3 or 4 weeks ago, we said that that a prime of x is given by the limit as h goes to 0 of a of x plus h minus a of x, all divided by h. And that leads us to what's called the fundamental theorem of calculus part 1. So suppose that we have this area function defined as before, so we have the area function is going to be the definite integral from a to x of f of t dt. X is somewhere in between a and b because that's where our area function is continuous. If we take the derivative of that area function, we get back the initial function f of x. Right? And that's what we get from right here. The derivative of this area function is just the function f that we started with. Okay, so let's go and do a couple of really straightforward examples. So we want to find the derivative of the area function that's giving us the net area underneath the function t cubed plus 4t going from minus 7 to x. From the fundamental theorem of calculus part 1, that's telling us that this derivative is just going to be x cubed plus 4x. The only real difference here is we switch the variable from t to x. And here we have that we want to find the derivative of the area function going from 0 to x of e to the minus t squared dt. That'll just be e to the minus x squared. Okay, and then there's also the fundamental theorem of calculus part 2. So now what we're going to do is we're going to really pull in the idea of an antiderivative that we had last time. So suppose that little f is a continuous function over the interval a to b, and capital F is any antiderivative of little f. Then the definite integral from a to b of little f is just capital F evaluated at b minus capital F evaluated at a. The other way that we could write this notation is capital F of x, and then we have this vertical bar which means evaluation, at b minus capital F evaluated at a. Now what's nice about this with capital F being any antiderivative is that we could just go and find antiderivatives like we did last time, but just set that arbitrary constant value to be 0. The reason why the constant value doesn't matter is that when you, if you make your constant, say, 27, when you have f of b, you're going to add 27, and then when you have the minus f of a, you're going to subtract off 27. So it doesn't matter what you pick for the constant's going to cancel out. So you can pick any antiderivative. The usual one is to just take c equals 0. Okay, so let's go and find some definite integrals using the fundamental theorem of calculus, just to wrap up. So I guess the one other thing that I can state here to make this nice is that the first part is telling us that the derivative of an antiderivative is the function you start with. The second part is saying that the antiderivative of a derivative is almost the function you start with. It's the thing you start with a slight twist, and that you're doing some evaluations. Okay, so if we want to find the definite integral for sine of x ranging over x equals 0 to 3 pi, we'll find an antiderivative, so minus cosine, and evaluate that antiderivative at 0 and 3 pi. So we'll get minus cosine of 3 pi minus cosine of 0. And in this case, what we'll get is that cosine of 3 pi is minus 1, so we get minus 1. Cosine of 0 is minus 1, or is 1, so we get minus 1 minus 1, which is 2. For these, keeping track of what's supposed to be negative and positive is also just something that you want to be cautious about. Okay, well, we could go and find the antiderivative from 1 to x of 2x minus 6. So this was the function for the region that had the triangle below the x-axis and the one above it. We found that the area from 1 to 6 of that function was 5, and conveniently what we see is that we're also going to get 5 out of this. So we'll find an antiderivative for 2x minus 6 from our product rule for our power rule for antiderivatives that we had from last time. We add 1 to the exponent and then divide by the new exponent. So our exponent was initially 1, then we add 1 to it and get 2, divide by 2. And then the exponent here is 0, so we have 6x to the 0, we add 1, divide by 1, and then evaluate this expression at x equals 6, subtract it off at x equals 1. And when we do that, we get 0 minus 5, which is just 5. Okay, well then how about for that trapezoid? So the antiderivative for 2x plus 3, we'll do the same thing. We'll use our power rule for antiderivatives, and we'll get 2x squared over 2 plus 3x. Evaluate that expression at x equals 4, subtract it off at x equals 2. When we do that, we get 18, so another way of seeing that the net area for that trapezoid region is 18. Okay, and then we also said that the net area for x cubed going from x equals minus 1 to 2 was 15/4, and what we see is, yeah, exactly using the notion of antiderivatives, we'll get 15/4 out of this one as well. So an antiderivative for x cubed is x to the 4 over 4, just from that power rule. We evaluate at x equals 2, subtract it off at x equals minus 1, and we get 4 minus a quarter, so 15/4. Again, exactly what we wanted. Okay, and then I'm going to throw in one example that's going to go and merge both the ideas of the fundamental theorem of calculus part 1 and also fundamental theorem of calculus part 2. So this one looks kind of strange. So we're going to find the derivative with respect to x of the definite integral from 0 to cosine of x of t to the 4 plus 6. So the first way I'm going to do this is with the fundamental theorem of calculus part 2, because we could easily find an antiderivative for t to the 4 plus 6 and then just do the evaluation and then take the derivative of that. So we could easily find an antiderivative for t to the 4 plus 6 to be t to the 5 over 5 plus 6t. And then we're doing an antiderivative here, so we're doing a definite integral. So we're going to evaluate our antiderivative at cosine of x and also 0. There's no problem at all with the bounds on the definite integral being some function. So like cosine of x, totally legitimate. When we put in cosine of x for t, we get cosine to the 5, cosine of x to the 5, all divided by 5, plus 6 cosine of x. And then we evaluate our expression at t equals 0, and we just subtract off 0. So our definite integral will be cosine to the 5 of x over 5 plus 6 cosine of x. What we wanted to do was find the derivative with respect to x of this definite integral, so we'll just go and find the derivative of this expression that we just got. Well, at this point we're using the chain rule, and we're old pros at that. So the derivative of cosine to the 5 over 5 will be, we'll take the 5 multiplied out in front, subtract 1 from the power, take the derivative of that inside function cosine, and get minus sine times cosine to the 4 of x, and then our derivative of 6 cosine is minus 6 sine. So our final answer that we'll get here is cosine to the 4 minus 6, or cosine to the 4 times minus sine, and then minus 6 sine. The other thing that we could do is we could use the fundamental theorem of calculus part 1. So we know how to find the derivative with respect to x of 0 to x of t to the 4 plus 6 dt. That's just apply the fundamental theorem of calculus part 1. That derivative would just be the this integrand x to the 4 plus 6. We also know how to find the derivative of cosine of x, right? Minus sine. We've done that a bunch. So let's use the chain rule. We'll define our outer function f to be this area function from 0 to x of t to the 4 plus 6 dt. It's maybe a strange outer function, particularly in the context of all the outer functions we've had up to this point, but it's a perfectly valid function. And it's an area function. It's a perfectly valid function definition. And then we've got this inside function, g of x, to just be this thing here, cosine of x. The other way to make sure that we've got everything right here for f of g of x is that remember that your function composition just means that everywhere where there's an x here, you're going to put in g of x. Well, the only x that shows up here is this upper bound, or the upper limit of the definite integral. So that's going to be the place where we're going to want to put g of x. So we're going to put it right here for cosine of x. Okay, so then we want to find the derivative of f of g of x. So we'll just use the chain rule. Our f prime is x to the 4 plus 6 from the fundamental theorem of calculus part 1, and our g prime is minus sine, something that we've done a bunch. So our derivative with respect to x of f of g of x is f prime of g of x times g prime. So g to the 4 plus 6 times minus sine, and g is cosine. So we get that the derivative is cosine to the 4 plus 6 times minus sine, which is exactly what we just found using the other approach of fundamental theorem of calculus part 2. So both of these approaches work really, really nicely, and especially they give us the same answer in the end, which is the ultimate ideal. Okay, so that goes and gives us the really, really useful theorem, fundamental theorem of calculus part 1. In the final video that we'll have tomorrow, I'll go and give kind of a wrap-up of a couple of more ideas with integrals. And then what I'll do afterwards is I'll go and I'll post a couple of videos into WIO courses that I did a couple of months ago that will also tell you how you go about undoing the chain rule and also the product rule. So far when we've been looking at antiderivatives, we basically only looked at the power rule and a couple of standard trig functions. So I want to give you a couple of more tools. You won't need them for a test or anything, but self-enrichment. Okay, and I will see you then. Bye.